Hey everyone, I'm Anup, and today I'm excited to talk about our work on contracts. It's a simple and intuitive abstraction that helps us reason about a variety of fundamental trade offs in congestion control. Now, despite decades of research in congestion control, we keep finding flaws in existing algorithms and come up with new ideas to fix them. We want algorithms that can generalize to a wide range of environments with different link rates, topologies, and links, and simultaneously optimize a variety of objectives like throughput, latency, and fairness. Unfortunately, we don't fully understand how these environments and objectives interact with each other and impose trade offs. For instance, Astria, a recent reinforcement learning based algorithm, works fine when the link rates are high, but starves flows on low capacity links. When we run 4 Astria flows on a 10 megabits per second link, one of the flows gets all of the throughput in the network. Similarly, AIMD on delay, which is a popular subroutine in many algorithms, works fine on simple dumbbell topologies, but it starves flows on more complicated topologies with multiple bottlenecks. Today, I'll talk about contracts, which is a simple and intuitive abstraction that helps us understand all of these issues and also predict them. We find that the bulk of these trade offs in congestion control stem from how these algorithms coordinate fairness with each other. Contracts formalize these coordination mechanisms and make these trade offs glaringly obvious. They help us expose various sources of severe performance degradation and allow us to build blueprints that CCA designers can use to better navigate the trade offs. So, what are contracts and what do I mean by coordination? Now, CCAs typically use things like probes to estimate quantities like bottleneck bandwidth or propagation delays and so on. Unfortunately, they can't do the same to estimate how many flows they may be competing with or what their fair share might be. And that's where coordination comes in. So consider these two examples here. I have 4 flows in the top scenario running on 100 megabits per second link with a fair share of 25, and 2 flows in the bottom scenario with a fair share of 50. Now, say the green flows in both these scenarios are sending at a fixed rate, which is 75 megabits per second in both these cases. Now, no matter how the red flow varies its rate or probes for capacity and whatnot, its observations, delays, losses, what have you, are exactly the same in both these scenarios. And from these observations, it cannot tell how many flows it may be competing with or what its fair share might be. Now, to get around this, what CCAs do is that they coordinate with each other by encoding information about fair shares into observable congestion signals. So if we were to run Reno on these scenarios, we'd see that the flows maintain a different loss rate in each of these scenarios. And by observing this loss rate, flows can infer which scenario they're running on and what their fair share is. Now, this can be a bit of a weird concept at first. If we think about it, if we had a centralized view of what's happening in the network, we would correctly set the rates to be fair share and have zero congestion. But CCAs deliberately create congestion and then use this to leak information to other flows. Now, in steady state, Reno maintains a loss rate that's inversely proportional to the square of the fair share. This is the Mathis model we've all studied in undergrad networking. We reinterpret this equation as the CCA's contract or its encoding of fair shares into observable signals and give a new interpretation of how CCAs reach fairness. So here I've just plotted the contract with loss rate on the x-axis and rate on the y-axis. Now, when flows are running on this network here, they have some current sending rate and are observing some loss rate. Now, to update their rate, flows use this contract to compute a target sending rate corresponding to their measured loss rate. Flows that are above target reduce their rate, and those below target increase their rate, so that eventually all flows converge to the same rate. Now, while I showed this interpretation for Reno, all congestion control algorithms coordinate in the same way. They all have a contract that is a function that encodes rate into congestion signals. So here I've shown contracts for some of the popular data center and internet congestion control algorithms. Now, even though I've shown contracts for all these algorithms, they're rarely an explicit design choice. Contracts emerge as an artifact of other design choices. And even when some of these designs do pick contracts explicitly, they don't fully consider what are the performance implications of these encodings. Across CCAs, we can see there's a wide variety in the contracts. They use different signals, delay, ECN rate, loss rate. They have different shapes, square, square root, and they have some shifts. When we studied the performance implications of these differences, we found a surprising result. This contract choice, one that most algorithms don't even make explicitly, fully determines most of the steady state performance metrics in congestion control. And since one choice fixes many metrics, we find that these metrics are at odds with each other. So specifically, contracts determine the CCA's throughput, latency or congestion, fairness, and also how well it can tolerate noise or diversity in network environments. And today, I'll show the tension behind three of these metrics, and this will also help us understand why Astria and AMD on delay, as I'd shown earlier in the talk, break or start flows. Now I'll use a running example of Vegas and Swift. Here I've shown their contracts with rate on the y-axis and delay on the x-axis, or queuing delay on the x-axis. Vegas uses a contract of rate as 1 over delay, and Swift uses a contract of 1 over delay squared. Now contracts determine how much congestion an algorithm must create in steady state. Now, since we're encoding rate into congestion signals, the range of link rates we want to support gets intertwined with delays we need to maintain. So if you want to support a 100x range of link rates, say from 1 to 100 megabits per second, then under Vegas, we need to make peace with maintaining a 100x range of delays from 5 to 500 milliseconds here. Now, if our contract is steeper, we can reduce this range. So with Swift, we only need to maintain a 10x range of delays, 5 to 50 milliseconds here. Now, this does not mean we can make this curve or contract as steep as we want, because steeper contracts then make the CCA more susceptible to noise and congestion signals. So if you look at these two flows over here sharing a bottleneck, one of the flows, the green one, is running on a wired link, and the red flow is running on a Wi-Fi link. Now, due to jitter in the Wi-Fi link, the red flow has a slightly higher estimate of the queuing delay. And due to the contract, this discrepancy in observed delays converts into a discrepancy in the steady state flow rates. And as we make the contract steeper, this discrepancy is larger, or worse is the robustness of the CCA to noise and the congestion signals. Now, this trade-off is the cause behind starvation in Astria. A lot of designs unaware of this trade-off try to unilaterally minimize latency. They think that, congestion should always be close to zero. After all, we're doing congestion control. But this is incompatible with how CCAs coordinate fairness. Specifically, Astria uses reinforcement learning. So it defines this fancy neural network architecture, network simulation environment, and so on. But when we look at its reward function, to minimize latency, it sets a zero reward whenever the delay is above a threshold 10 milliseconds. And to honor this reward, the training process learns the following contract. Here, all of the rates between 0 and 10 megabits per second are encoded in this narrow band around 10 milliseconds of delay. Now, this is a bad contract that causes extreme unfairness whenever the fair share is in this region. For instance, we ran 4 Astria flows on a 10 megabits per second link, and the fair share is around 2.5, as shown as the point in the figure. And we find that the flows do maintain 10 milliseconds of queuing in this case, which is consistent with the contract. However, due to ambient measurement noise, one of the flows interprets this 10 milliseconds as a fair share of 7, while the others interpret it as a fair share of 1 and almost starve in comparison. So that was latency and robustness. I'll briefly describe how contracts also determine fairness on multi-bottleneck topologies. So by multi-bottleneck, I mean topologies where queues may build up on multiple hops on the path of flow. A simple example is a parking lot topology. Here, the red flow sees congestion signals at 2 hops in the network. Such a situation can commonly occur when multiple interpod flows contend on a typical data center topology. Now, on simple dumbbell-style topologies, fairness is simple. We want flows to have the same rates. On parking lots topology, the situation is a bit more nuanced. We have multiple notions of what it means to be fair. If we still want all the flows to have equal rates, that's typically called as maximum fairness. Another notion is proportional fairness, where since the red flow utilizes twice as many network resources, it gets half as much network throughput. Now, you and me can go on and argue about what notion is good, but the point I want to make is that by choosing a contract, we're also effectively choosing the fairness notion that applies on these topologies. Going back to our example with Vegas and Swift, the red flow sees the sum of the delays seen by the blue and green flows. Now, same as before, this difference in observed queuing delays translates into a discrepancy in the flow rates, and steeper the contract, higher is the discrepancy, or worse is the fairness. Now, with this, we can also understand why AIMD on delay starves flows on parking lot topologies. So while in Vegas and Swift, we encode fair shares into the magnitude of delay, AIMD on delay encodes fair shares into the frequency of delay. It maintains a steady state sending rate that's proportional to the fraction of time delays below a certain threshold. And this is what causes AIMD to starve. So if we look at the execution here on the parking lot topology, flows are additively increasing their congestion window whenever the delay is below 50 milliseconds, which is the threshold, and cut their window in half otherwise. Consequently, the blue and green flows oscillate their queuing delay between 25 and 50 milliseconds on their respective hops. Now, the red flow observes the sum of both of these delays, which is always above 50 milliseconds. Consequently, it has no incentive to ever increase its congestion window, and it starves. Now, this was just a glimpse of reasoning we can do using contracts. They helped us expose similar issues in a variety of other algorithms, including SMART and STRAC that are being standardized in industry for AI networking stacks. Now, to systematically avoid all of these issues, in the paper, we give a blueprint that designers can follow. We take a deep dive into how different aspects of contracts affect CCA performance. We look at the impact of using different congestion signals, changing shape, shift, and intercepts in the contract. We discuss dynamics and RTT unfairness and more. To conclude, I introduced the concept of contracts and showed how CCAs use them to coordinate fairness. Contracts help us quantify performance trade-offs, expose performance mistakes, and build blueprints to guide CCA design. For any new algorithm that you're designing or analyzing or even reviewing, I urge you to ask yourself, what is the contract for this CCA? And I guarantee you that this will vastly improve your understanding of how that algorithm really works and what trade-offs it is making. With that, I'd like to thank you all for your time and attention.